Hi, this is homework 4, part B1. And here we are going to have a variable volume, constant cross-section, and a perfectly stirred tank. So we can go ahead and draw our tank. And we know that it is going to have some flow in and some flow out. And we can draw a liquid level. And we have time varying with inlet flow and concentration. So for this problem, we are going to be deriving the differential equations for the concentration and the liquid level in the tank. So to start, we know that we have some height for our liquid level, and we can denote that H, and that we have some concentration in our solution. So we can just write that as Ca. And we know that we have some flow in, so we can write Q in, and then we also have some concentration in, Ca in. And continuing on, we have some flow out, Q out, and since we also have a perfectly stirred tank. So now that our tank is stirred, we have the same concentration that we have in the system. Since it's stirred, that will be the same concentration leaving the system. So we can write that as Ca. So since we have a variable volume, we know that we need to look at the change in volume with respect to time. So we want to go, the differential of volume with respect to time is equal to the flow in minus the flow out. So now that we have our differential equation set up, we need to go ahead and do some manipulating to get it set up for the system that we have in this problem. So we know that we have some cross-sectional area, so that we are going to need to multiply that by our differential of volume with respect to time. So continuing on from here, we need to think about our Q out value. And looking back at our part A1, where we derived the inflow and outflow of the 3 system tanks, we know that the outflow is equal to the drainage hole area times the velocity, which is 2 times GH. So now that we have our Q out value, we can rewrite this expression. As the cross-sectional area times the differential volume with respect to time is equal to Q in minus the cross-sectional, or the drainage hole area times the square root of 2GH velocity. So this is our equation. So our next step is going to be dividing by the cross-sectional area. And that gives us this. So now that we have came up with a differential equation for our variable volume, we are now going to want to look at the rate of change of the moles in our system, so that we can come up with a differential equation for our concentration. So what we're going to want to look at is the change in moles over time. And so we know that this is going to be equal to the inflow minus the outflow. But since we're looking at moles, we are also going to want to include our concentration in and the concentration that we are still left with. So this gives us Q in times our concentration in minus Q out times that concentration. So once we have this step, we want to try to change our terminology here. Instead of using moles, we want to use an expression that we know, that is moles is equal to the concentration times the volume. And using that, we can do some massaging and just put that in here. And doing so gives us the rate of change of our concentration times volume over our differential of time is going to be, again, equal to this expression above. But we know that volume is going to be equal to the height times the value of the cross-sectional area. So using this, we can go ahead and derive this further to get that we need to multiply this by the cross-sectional area. So now that we have our cross-sectional area multiplied by our differential expression, I'm going to go ahead and rewrite this out from above. Those are rate in times our concentration in minus, and I'm going to rewrite our Q out as I did in the previous derivation as the drainage hole area times our velocity. So minus AD times our square root of 2GH, and that is again going to be multiplied by our concentration. So now that we have this, our next step is going to be dividing this expression by our cross-sectional area. So next we are going to try to break up this left side of our expression by using the product rule. And doing so will give us C, our concentration, times the differential of height over time. And then that will be plus our height times the differential of our concentration over time. And then that is going to be equal to the right side again. I'm just going to write equal to that still. So from there, now that we have that, we are going to want to subtract the concentration with dH/dt to our right side, which would leave us our height times the differential of our concentration over time is equal to Qn times our concentration in minus the drainage hole area times velocity times concentration. And I'm gonna rewrite this as 1 over the cross-sectional area, and then this is also going to be subtracted by our concentration times differential of height with respect to time. So our next step will be to try to incorporate this expression into what we had up here on our left side. So we can rewrite this as our height times the differential of our rate of change of our concentration over time is going to be equal to 1 over our cross-sectional area times the rate in times the concentration in minus the drainage hole area times the velocity, and then times the concentration, and then incorporating this in will give us minus the concentration times the Qn, because it's just incorporating the outflow, and then we are going to take minus Ca times the Qn, and then that is going to be plus the concentration times the area of the drainage hole times the velocity. So doing that will give us the concentration of times the area of the drainage hole times velocity, and then we'll close that off. So this expression is what we derived from splitting this up from the product rule and reincorporating that into the right side of our equation. So the next step that we're going to want to do is divide height on our right side to cancel it out. So doing that, we can just write our cross-sectional area times the height. So looking at our expression here that we have derived, we notice that this term and this term are opposites of each other, so when we add them together, they just cancel out and go away. And we notice that in this term, we have our rate n constant in both. So what we can do there is pull out the rate n, and we can express this as such. So we have the differential of our concentration, the rate of change with time, is equal to our rate n over the cross-sectional area times the height, and then this is going to be multiplied by our concentration n minus our concentration. So this is our derived differential equation for our concentration in this system where it is perfectly stirred. I will now be implementing these derived expressions into Google Colaboratory to come up with some numbers for our problem, and so that we could see them in real time.
This is homework 4, part B2, where we are going to be starting from an initial steady state where the flow into the tank is 0.1 meters cubed per second with a concentration of 1 mole per meters cubed. The inlet flow rate increases by 10% while the inlet concentration increases by 25% at t equals 0. If the tank has a constant cross-sectional area of 1 meter squared, a drainage hole of 0.01 meters squared at the bottom, simulate how the concentration and liquid level evolve over time. So to start this one, we are going to head over to Colaboratory and import numpy as np, and we're going to go from scipy.integrate import solve IVP so that we can solve our differential equations. And we're going to go from plotly.subplots import make subplots so that we can plot our results onto a graph. Shift enter. Good. Okay, and now we are going to initiate our knowns that we are going to be using and pulling from so that we can solve our equations. So to start, we can go ahead and label G for gravity as 9.81, and then we can set Qn naught as 0.1, Qn naught, which is just the initial value for Qn, 0.1, Next, we can set our concentration as 1 mole per meter cubed, and we can label this as our Ca naught, for our initial concentration being 1. Next, we know that our inlet flow increases by 10%, while the inlet concentration increases by 25%. So we can label Qin as Qin naught times 1.1 for the extra 10%. And we can label our Can as our Ca naught times 1.25 for our extra 25% at T equals 0. Next, we are going to want to input our cross-sectional area and our drainage hole. So we can label our cross-sectional area as AC, and that is equal to 1. And our drainage hole area is 0.01. And we can also input a time for our simulation to end, and we can just make that 1000 for now. Shift enter. Now we are going to make a statement for our initial height value, which we derived in the previous part. So we are going to call h naught, and we are going to set that equal to our Qn naught value, and we're going to square that and then divide it by the drainage hole area. We are squaring that and then multiplying by 2g, and we need to put this in parentheses. Okay, so that's our h naught. Shift enter. Next, we are going to define our differential equation, which is our differential of volume over time. So we can go dv dt is equal to, we're going to define dv dt, and we are going to have our x and t and h as our second variable. And then we can go ahead and then from here we can go and label our height and our concentration, and we can call that a V just to make it a one grouping. Enter. And also in this definition of our differential equation, I am also going to make a statement which provides the expression for our Q out value. So we can go Q out is equal to the area of the drainage hole, and then that is times the square root of 2 times G times H. Times H, and then this is raised to the 1/2 for the square root. Next, we are going to input our differential for the height with respect to time, and we can set this equal to the Q in minus Q out, and then that is going to be divided by the cross-sectional area, and that was also previously derived in the previous parts. Next, we are going to input the rate of change of our concentration over time, and we can call that as dCA dt. And we're going to set that equal to Qn divided by the cross-sectional area, and that is also divided by H, and then this is going to be then multiplied by the concentration N subtracted by the concentration. So once we have all of those statements listed, we are going to want to then return our dH dt and our dCA dt, which were our two functions that we had derived in part B1. Shift enter. Now we are going to want to use the solve IVP function, and to do so we are going to want to create a vector, and we can go vec is equal to solve underscore IVP, and here we are going to want to be solving our differential of volume with respect to time, and then we are going to have a time span from 0 to what we listed before at the top, t end, and that is just for the range of our function to run from 0 to 1000. And here we are going to label our initial values, and we are going to have H naught and our initial CAO naught for our initial values of our liquid level and concentration in the system. And as we did in our previous coding in part A2, we are going to need to use our dense output function in order to integrate a system with a initial value. So we can set that as equal to true. Now we can go ahead and get out of there and go shift enter. Now we can go shift enter. I just had a wrong letter in here, but I got that fixed now. So we can go shift enter. Now we are going to want to set up our plot as we did, and we are going to use np.linspace, and we are going to 0 to t end, and we will want it to go to 500. Okay, now we can input our H and CA. We're going to want to unpack that because we have been using a V. So we have H comma CA is equal to vec.sol, and that is just going to be solving the initial value problem and putting the solution on our plot. Shift enter. Now we are going to create our plot, so we can go fig is equal to make underscore subplots, and here we need to make rows equal to 1 and columns equal to 2. And we need to do that because in this code we are setting it up to solve for two different values from the same line of code from the initial value problem. So our height is going to be our rows 1, and the concentration is going to be the columns 2. And from here we can go fig.add underscore scatter, and our x here is going to be the t plot, y is going the h, the name is going to be, this is going to be the first one, so we're going for height, and then after our name we have mode, and we are going to want lines, so that'll put lines on our plot, and we need to row is equal to 1 and column is equal to 2. So after we get that, we can go ahead and copy this line because this one was, and now we need to make one for our concentration. So we are changing our Y to CA. We're changing the name to concentration. And then after we get that changed, we can go ahead and run this and create our plot. Shift enter. So I got my plots on the same one, so I'm going to try to change our column here to 1. We go shift enter. So I made this column 1 and this column 2, and I hit shift enter, and here you see our plots for our height and concentration. And if you notice here on our concentration, our value sort of oscillates around the value of 1.25.